Hello everyone, this is a problem on the static force and circular motion. So let's start with it. Here's the problem. A ball is suspended from a string and after being given a push moves along a horizontal circular path. The length of the string is L and the angle made by it with the vertical component of weight is theta. It takes t seconds for the ball to make complete circular trip. From these measurements, we need to determine the gravitational constant small g. So let's look at normal figure. There is a string and the ball is attached to the string and the string is attached to a ceiling and the ball moves in a circular motion. So when we resolve that into a free body diagram, we get the diagram which describes the ball. There are several forces acting on it. The first force is this weight which is acting downwards, and there is the resultant of that force of that weight towards the y directions, and there is also an angle made by y direction with the length of the string, and we have tension, that is Ft, on the string acting towards the ceiling. So when we resolve this force, the tension, into its x and y component, we have L cos theta towards the y direction, negative y directions, and L sin theta towards the x-axis, which is also the radius of the string, or we can say the radius of the circular path made by the string. Let's say the resultant L sin theta as equation x, which we will use later on with this problem. So at first we need to reinstate the momentum principle, since we will be using that concept. We have a unit vector Ft, which is given by the angles made towards each axis, sine theta for x-axis, cos theta for y-axis, and 0 for z-axis. And when we try to get the vector component of the force tension, we have the magnitude of the tension times F cap, which is the unit vector. And now when we resolve this vector for the total force, the total tension of the string, we get Ft in the magnitude times sine theta on the x-axis, Ft cos theta minus mg on the y-axis. Remember, we have a weight that is acting towards the negative y-axis, hence when we move towards the positive y-axis we have to cancel out that mg. That's why we subtract that mg, and then we have 0 on the z-axis. So for the parallel component z-axis, the net force is 0, so we don't have to worry about that. So for perpendicular components, there is y component, and the y component, as we have already reinstated before, is given by Ft cos theta, which is the resultant of the tension of the string towards y-axis, minus mg, since mg is a force, a weight that is acting towards the negative y-axis, and to balance that we have to subtract that weight. So we know that change in momentum is equal to 0 according to conservation of momentum. So from that we get Ft equals to mg cos theta. Now we suppose that as equation 2. After that we need to get the x component, and that is given by Ft sin theta, as we have calculated before. Now as we move the string towards the center of the circle, we get to know that the x component balances the centripetal force, and it helps to maintain the string in its uniform motion. So this is given by mv square by r, mv square by r being the centripetal force equals to Ft sin theta being the x component. So we need to get the value of r, that is L sin theta, from equation 1 and plug it into the second step, and then we need to get the value of Ft that we get from equation 2 and plug it into a second step, and then solving that we get small g equals to v square cos theta by L sin theta whole square. Thank you.